Rust has two powerful features that allow you to avoid rewriting lots of boilerplate code. The first is generics, which work much like templates in other languages like C++. They allow you to change the type of accepted values in function parameters, return types, and even structs and enums. The second is traits, which work like interfaces in other languages. They act as contracts to define shared behavior among types. We'll see both of these in action throughout the episode. We previously saw how to work with the I2C driver to read from a temperature sensor. We're going to take a step back to examine generics and traits in Rust without touching embedded code. At the end of the episode, I'll show you an example of how you can use them to wrap up a simple LED driver. Let's get started. To start, let's create a new project in our apps directory. We'll give it the name generics example. We'll set it to binary for executable and version control system to none. Let's refresh our files here. We should see generics examples. Let's go to source and go into main.rs. We are not going to be looking at embedded code right now. This is just going to be basic Rust on our operating system. Let's start with an example of using generics for a function. Rust is a strongly typed language, which means we have to declare the types of all variables, parameters, and return values. As you have seen, yes, some of the types can be inferred by the compiler, but it's still a strongly typed language. Let's take a look at this function where we want to, say, swap two items in a pair, and we'll set this as a tuple. So our pair is going to be an I32, or signed integer 32 bits for our first item, and a string slice. We're going to return the swapped version of that, so string slice and I32, and all we're going to do is take in those values and just return a tuple with the first item, comma, the second item. Notice we are explicitly calling out the types here for the parameters and the return types. Let's create a quick demo where we have an original tuple, that's 42, hello, that's our string slice. We will call the swap function, pass in that tuple, get a tuple in return, and we will just print that out. So save this, go into our generics examples, let's say cargo run, that should build it, and print it out. Sure enough, the values have been swapped. Okay, this works great for this very explicit statically typed parameter set and return types. What happens if we want to use something else, like a float or anything else? So if we try to put 4.3 in here, we'll try to run this. We get an error because 4.3 is not a string slice, that's a float. In fact, it's saying that right here. So how do we deal with this? Well, let's create a new function where we use generics instead. We've come across this syntax in previous episodes. We're going to use angle brackets to declare the generics. In this case, after the function name, we'll say that there are two generics we care about, so we declare them capital T and capital U. By convention, Rust uses single letters with capitals, generally starting at T for type, to denote your generics. This works much like templates if you're used to using those in something like C++. As we did before, we will declare our parameter, the single one here known as pair, and then we give it the types. Instead of, say, I32 and string slice, we're going to use T and U because those are the generics, the generic types that we just declared right after the function name. So now it accepts a tuple of type T and type U, and those can be pretty much any type, including things like structs and enums. We are also going to return a tuple with T and U, but remember we've swapped those values because that's what this function is doing, so it's now U, T. Let's save this after we have returned pair.1 and pair.0, and let's go ahead and run it again. Sure enough, the compiler figures out that T and U should be an integer and a float, and it handles that appropriately by assigning T and U to those specific types. With Rust Analyzer and IntelliSense working, we can press Control and Alt to get the types. Sure enough, I32 and F64. Let's change this back to the hello string, or in this case, a string slice, and you can see that the types are automatically updated. The compiler infers those, and because we're using the generic, that updates to I32 and string slice as well, automatically when we compile. So let's save that. We'll run again, and sure enough, this works just fine. Something to keep in mind here as we're going forward is that the compiler performs something known as monomorphization. That is, as the compiler goes through, it sees that we are calling swap, and it needs to create a version of swap with i32 and a string slice for t and u, so it actually generates a new function with those concrete types. So if we use it again with a integer and float, later in the code, it would generate another one. So every time you use a version of a generic function with concrete types, the compiler actually generates code for each of those types. So right now we only generate one function, but if we had another one where we used a different set of types, another function would be generated on the back end. This is how you can run into some code bloat if you start using generics a lot and with different concrete types. Next, let's talk about traits. A trait is a contract. It defines what methods a type must implement should they implement that trait. This is similar to things like interfaces in other languages. To do this, we first define the trait, and then we will define the type in a moment, and then say we will implement that trait for that type. But to define the trait, we just say trait, give the trait a name, in this case hello, with a capital letter by convention, and then say what function or functions need to be implemented in that trait. In this case, just one function, say hello. We give it a signature. In this case, it will accept a reference to the type itself, so like a struct or an enum, and we won't have a return type here. Then we will define a type. In this case, it's just a custom struct named person, and it's more or less just a wrapper for this string, which we will say has the variable name. Right now, the trait and the struct are not related to each other. Next, we will implement the trait for the type. We will do that with the keyword impl for implement. We're going to say, hello, we're implementing a trait, and we're going to implement it for a type. This means that our type, person, this struct person, must use the functions set forth in the trait. This is why you were seeing things in the documentation earlier that would say certain functions like I2C functions are implemented for a particular type, like an I2C bus. A lot of the HALs for embedded code implement various traits so that they all have the same function signatures, even if the definitions are different on the back end. That's how we can swap out, ideally, different HALs, and they should more or less function the same because they all implement the same traits. They all have the same interfaces. So to implement the function given by that trait, we have to use that exact same signature. So function say hello. So instead of a semicolon, we'll put curly braces because we're implementing this function instead of just providing a declaration inside of a trait. All we're going to do in this function is just very simply print the name that's stored in the struct. Now let's see this in action. So we're going to declare an instance of this struct. We'll say let me, that's the name, equal person, that's the struct. And we're going to define the only value in there, which is name, and we're going to give it my name string from Sean. Because we've implemented that definition, we can say me, which is the struct, dot say hello, which is going to call the function associated with that struct. Let's save this. And let's call cargo run. That should build. And sure enough, it says hello and give the name of the struct. All right, let's move on to trait bounds. Let's create a very simple function. We'll call it add. We'll give it the generic t, and we're going to say as long as a and b are the same type, let's go ahead and add those together and return whatever that sum is. Notice there's no semicolon here, which means this effectively returns the output of a plus b. All right, let's try to run this and see what happens. So we're going to cargo run. And we get this error, cannot add t to t. Why is that? It's going to give us a hint what we should do here, but let's focus on what's going on here. As you can probably guess, some operations are not supported for all types. Because this is a generic, the compiler has to go, okay, this should work for things like strings. And the addition operator is not supported for things like strings, at least by default in Rust. So it gives us this error, I don't know what to do with this, because I can't just add anything to anything. Other languages often solve this problem using something known as duck typing. For example, Python and JavaScript, they assume that the types implement the required functions, and they just try it. If it looks like a duck, quacks like a duck, probably it's a duck. So these types of generics will often just work, or you don't have to define the generics because it's a weakly typed language and it'll just accept any parameter values. and it just attempts to perform this operation. If it fails, it actually fails in runtime and throws an error. C++ uses a version of compile time duck typing where it generates an error only when you try to instantiate the template with an incompatible type. But in Rust, we have to be explicit about our types and what operations those support. So we can bound where our add function can be used and on which types specifically. Let's make a note about what causes the error here. And we're going to recreate our function where we're going to add a trait bound. Trait bounds are given by the keyword where, and it's part of the signature here. So you see I haven't opened the curly brace yet. We're going to give it the type, so type T, and then the bound. And we're saying here that this function add only works on types T that implement the add trait that's found in the standard library. So the plus operator. Note that we are putting this bound on type T, which means it also affects the output or result type as well. This essentially says that this function will work on all numerical types, assuming that A and B are the same type. So things like integers and floats. It does not work on Booleans because Booleans do not implement this add trait. And as you can see, sure enough, add is indeed a trait. Strings are a little tricky. You can use the addition operator to concatenate a string with a string slice, but not two strings together and not two string slices together. So you would need two different types here for A and B to support strings. We're just going to ignore that for now to keep this example very simple, but you could create a new version with two types to concatenate strings together. And then also note that you can specify multiple trait bounds, hence the comma here, where needed. But we're going to leave it at one trait bound, and we are going to implement A plus B just like we did before. And it looks like I misspelled output, so let's correct that spelling. All right, let's save this, and let's try running it again. Sure enough, this works. We can add these two numbers together and get an output of 7. Let's make a note that this works for I32. Let's try with floating point values. We'll run that. Sure enough, we get that correct output. As I mentioned earlier, this should not work with Boolean values, so we'll save and run that. We'll get this error cannot add bool to bool because there is no implementation for bool plus bool, because Booleans do not implement this trait here, this add trait. So that does not work. Let's try it with string slices. And as I mentioned, that there's no implementation for string slice plus string slice. So this does not work either. Let's make a note there, and I will comment this out. And now you have a working example for trait bounds. All right, let's move on to number 4, where we can see how generics can get used in structs in addition to functions. You've probably already seen this with the result and option types. Those are generics, and we can define a custom struct here called pair. We will declare our types, T and U. Those are generics, so those can be any concrete type. The first value will be of type T, and the second value will be of type U. Now we're going to provide an implementation of various methods for this struct. So the struct can hold data, and it can also perform actions using these methods. You'll find this pattern quite a lot in Rust. This is very similar to a constructor used in object-oriented programming languages like C++. We're going to manually define a new function here. That's going to be a method that's part of this pair struct. You will need to give it the first and second values. Note that those are types T and U, as we declared earlier, and it's going to return the actual instance itself. So whoever is calling this will have ownership. And we're just going to construct an instance of pair, pass in first and second, let the types fill out where they may for first and second, or for T and U, and then the caller will have an instance of that struct. And just for fun, let's implement another method here just to see how this works. We will recreate our swap function, but as a method that's part of this struct. In this swap method, we will put self as a parameter because this method actually takes ownership of the calling struct. It's going to use the information in that struct passed in, swap the first and second values, and then return essentially a new instance of the struct with those values swapped. So note that we have to return pair type u and t instead of t and u this time. And then in the new struct that we're constructing, we'll just assign first as the self.second and second as self.first. And that instance gets returned. So in our main, we're going to call pair. That goes into the namespace of that pair struct, allows us to call the methods in that struct. So new will pass in 42 as our first value and hello as our second value. Those types get automatically filled out. Well, actually, the compiler performs monomorphization, which generates concrete types of these structs and functions for, which should be integer 32, and a string slice. Then we will call swap on that collection to get a new pair with the first and second values swapped. Let's print the first and second values of that swapped set, which should be reversed from that first collection we created. Let's save that and cargo run. That should compile, and sure enough, hello comes first, even though it was second in the first, and 42 comes second. All right, let's remove this, and let's move on to generic enums. This is similar to declaring generic structs. All right, let's create something called maybe. We're essentially going to give a demonstration of how the option T enum works in core Rust. Option T looks like this. It's the enum value sum with the generic type T, and then none, which is just another enum value, but it doesn't hold any other type. It can't hold any other information. By default, Rust does not have a null or none type built into the language like you might find in like C++ or JavaScript or Python. This is to help prevent some memory errors, but it does have this option enum where it wraps up values into this enum. So sum contains the value you actually want, and none means, well, none. This is essentially a placeholder for null or nothing. Let's create a very simple function. So we have to call an implementation for our enum here. We're going to recreate the unwrap function that we saw for things like options and results, so you can get a sense of how those are implemented. So our function signature will consume self, the instance of the enum, and it will return type T. That's the same type T that's being held in that something value. A quick note about enums in Rust: you must explicitly list out all of the variants or options in that enum. Otherwise, you will get a compiler error. So inside of unwrap, we're going to call match on self if that is of type maybe something, so that something variant in maybe. Get that value and just return the value, so hence type T. Or if the value is nothing, actually crash the program, call the panic handler, and give it the error message of call to unwrap on nothing. This is a very simplified version of what's going on in unwrap under the hood of unwrap in the core library. So in our main, let's instantiate some things here. So we will say let no value, and I need to actually make this a type. We will make it a type of maybe string, so T becomes type string, but then we're going to set it to the variant nothing here. We will also create another enum that is of type F64, so notice that we have to use the angle brackets to create a concrete type for maybe here, and we will set maybe something, and we will have something hold 1.2345. That is a floating 64-bit value. We can use the match function to check manually. So we will match no value. If that is equal to something, we will get the value in that something and just print it to the console with value in front of it. If the variant is nothing, we will say no value found. So we can execute these statements and not do anything with return values if they return anything. Or if we happen to know that it's probably not nothing because that would crash our program, we can call unwrap here, and that's what we've been doing in our embedded code. Rather than checking manually with this match statement, we can just call unwrap here, and that will get the value in some number, return it so that it fills out the unwrapped value, and that should print out the floating point value for us. Let's save, and we'll call cargo run. Sure enough, no value contained nothing, so then it printed out no value found thanks to this match statement. And then we printed out the value that was stored in something here, and we got that value by calling unwrap, because if we just try to call some number, you can see we get this error because maybe does not implement the display trait. So it has no way of printing that. So let's just keep unwrap in there, and you have a working example on using generics with enums. Let's see how we can apply what we've learned with generics to some embedded code. Let's close down our example here. I'm going to clear our console. Let's copy Blinky, make sure there's no target folder. So let's delete that. Just makes copying go a little bit faster. We will copy Blinky, we will paste it, and we will rename it to LED wrapper. In here, let's go to source main. So this is the Blinky example we wrote in the second episode. Let's scroll down, and we will create our struct after we set up our constant values here. So let's create a generic LED struct. This is going to be a very simple wrapper that we can give it some functions like on and off, and it knows what to do with that based on the pin that we've defined. So if you remember, those pins are actually generics. So we can take whatever concrete type we've defined for the pin and set it to the pin of our LED here. And just for fun, let's add another value here called active high, whether you've connected the LED to ground or you've connected the LED from, say, high through a resistor to the pin. So if it's active high, we toggle the pin high in order to turn on the LED, and if it's active low, we toggle the pin low to turn on the LED. And we will implement that switch here. So we're going to provide an implementation of our LED struct where we give it some methods. So we will declare this as a generic implementation. We will use P as our type. And we're going to give it a trait bound here where we say that this will only work where P implements the output pin trait. Because if it's set to an input pin or something else, we probably should not be toggling that pin anyway. I've been using the where keyword to be explicit, and it's useful when you have multiple trait bounds you need to list out. You will often come across this shorthand inline version of a trait bound where you say impl or implementation P colon and then your trait bound, so output pin, and then you give the struct its name and then list the type P. So if you see something like that with the colon, knowing that P is a generic, that output pin is a trait bound. This is equivalent to using the where keyword that I used below in my actual signature. So this is equivalent to this. Let's create our faux constructor here. We will say function new, pin is of type P, active high is of type bool, as we saw earlier for our struct. We will return an actual instance and ownership of that instance, where we just assign the pin and active high arguments passed in. So now we'll define a function called on. We'll pass in a mutable reference to the struct, and in that reference, if active high is true, we will say pin.setHigh and then unwrap that value. So this will panic if some error occurs trying to set that pin high, or if it's active low, set the pin low. This should turn the LED on. We're going to do the same thing with the off function, but if it's active high, set the pin low, and if it's active low, set the pin high. This should turn the LED off. All right, let's scroll down to our main function. We'll set up our clocks, get the SIO, split off ownership of the peripheral struct. We're going to set up our LED pin, and this is where we're going to use our wrapper. We're going to say let mutable LED. Remember, we need mutable because we do need to change the internal values of this based on the changing of the internal values of the LED pin that we've passed in, and that is also mutable. We're going to say LED new. We're going to pass in ownership of the pin, and we're going to set it to active high because that's how we have connected the hardware. Then in loop, we're no longer going to manually toggle the pin. We're going to say LED on, and we're going to say LED off, of course, with semicolons. That's using our wrapper, which was based on a generic type, based on the pin. And if I refresh the Rust Analyzer server, I can press Control and Alt. You can see that the pin actually changes type here. This concrete type is based on the GPIO number we set here. So if I used a different pin, this type would actually change. And you can see I'm getting a warning here. It would compile, but it does not need to be mutable. So I can take back my statement about LED pin being mutable because we passed that in and we still maintain that LED is mutable. So something is changing, but we just care about LED being mutable. All right, so in our terminal, let's go out of generics examples. Let's go into our LED wrapper. Let's say cargo build and wait for that to compile. And we're going to use Pico tool UF2 convert. We'll give it target, go into the thumb v8 folder, debug, and it looks like the elf file is named Blinky because I forgot to change the name of the project in cargo.toml. That's fine, it's still a Blinky program. We'll give it the input type of elf, and let's dump it into firmware.uf2. Looks like I messed something up here. All right, I just reran it. I think there was a value after elf that it didn't like, so reran that command again. That seems to work. Let's hold the boot select button and plug it in. Let's go into our repository, workspace apps. We've been working with LED wrapper. There's firmware.uf2. Copy that and paste it into the mass storage device drive that appeared. You should see the LED blinking on and off. In the next episode, we'll put everything we've covered so far into practice to write a simple driver library for our TMP102 sensor. Feel free to review anything up through chapter 10.2 in the Rust book. Hopefully, Rust is starting to make a little more sense now that we've covered many of the basics. You'll get a chance to put it all into action next time. Stay tuned.